Yeah, you can start if you like.
Okay, thank you. So thank you so much, Nicola, for the invitation again. It's already a pleasant tradition. So as you have probably read, I will be and heard from Nicola, I will be talking about colors. Okay, the Exodromy theorem. Okay, so this is a theorem in topology, algebraic topology, let us say, with a very clear categorical flavor. So essentially, I will state the theorem at the end of the talk, but it says that you have a category of sheaves, which has a clear geometric interest, and you can deduce categorical properties for this thing from a very explicit presentation of this category. Okay, so it will be a category of functors in a way that I will specify later. So, section 1, categories of functors. Of course, every category is a category of functors, but that's not what I have in mind. So, example, presheaves on a topological space with values in some category B are defined as functors from the category of open sets of X to B, contravariant, of course. Good. So essentially, the spirit of when I will talk about categories of functors is that the topological information, so the topological object, is in the source, and coefficients are in the target. I will be more clear later. So let X be a topological space again, with additional data or structure, and let's call this additional datum S. Of course, this is a very generic and perhaps uncomfortable sentence. What's an additional datum? What's additional structure? Everything will be more precise during the rest of the talk. So, for example, so S could be a closed subset Z in X, or stratification of X, or you may also be wanting to think to, I don't know, a group action on X, and so on. This is a more complicated setting. So what we will be interested in is the second example, but with time. So we can consider, in this setting, we can consider sheaves or presheaves. We will be more interested in sheaves on X, satisfying some property with respect to S. So let me make an example. Sheaves with coefficients in vector spaces or some field with support in Z. Okay, this form a category if you want, a subcategory of the original one. or so the category of sheaves or oppressed sheaves on X with coefficients in vector spaces, or what are called locally constant sheaves. So in this case, there is no structure you have to add, so S is nothing, but there is a property. So our sheaves, which are locally constant. So for every point, there is a neighborhood where the sheaf is constant. Or a slightly more complicated notion, which is what we're interested in, constructible sheaves. With respect to stratification S on X. So what's the stratification? Will be more precise in the actual mathematical part of this talk. But stratification is a partition of your topological space into locally closed subspace in such a way that you can define constructible sheaves to be sheaves that are locally constant on each stratum, where a stratum is one element of this partition. But I will give this definition again. This is just to familiarize with what I mean when I say structure and property. So in any of these examples, we are dealing with a category of the form sheaves over X S with coefficient in some category B, satisfying the property P. Let me use this notation. Great. Question, which will lead us to the actual mathematical part. Question, when can this category, sheaves P, X, S, B, be expressed as a category of functors? What do I mean by this? As something of the form C equal to functors from A depending on X and sorry, X and S with coefficients in B. Sorry, this is just a comma. Okay. Where AXS depends, as you can see, on X and S. But B does not. This is just a category of coefficients. Okay, this is what I mean by category of functors in our setting. So something where all the geometric information is concentrated on the source. This is very rare in principle. So for example, I mean, take any subcategory of your category of sheaves. How can you know that this subcategory is, again, let me say, representable? So co-representable in this case, right? So there is some actual co-representative of your category of function, of category of sheaves, or your theory of sheaves. Of course, this is not true in general. But if it is true, what are the advantages? And let me anticipate that our exodromy theorem will be exactly a result of this kind. That some subcategory of sheaves is co-representable in this way. So advantages. So first advantage, probably the most important, if B is presentable, for example, or I don't know, abelian, or other properties, let me put also stable, which is something that makes sense only for infinity categories, but I will not talk about this. Then our category is as well, right? because these are properties that can be checked on the target category if your category is a category of functors. And this is actually something I used in my research. Of course, I don't have time to explain exactly what I used or where I used it actually, but it's a very, very useful property and can be formulated in purely categorical terms like I just did. Now, another advantage of this is that the association XS going to sheaves with the property P is symmetric monoidal if XS to A of XS is, because you can prove that, yeah, at least when B is presentable, but I don't think this is necessary, you can deduce properties in the world of being symmetric monoidal, being lax monoidal, being O monoidal, where O is an operand, from something you know on the source, right? So really, having your category of sheaves expressed as a category of functors is extremely useful. And this second property is something I used as well in my work. So I had a category of sheaves, constructible sheaves, which is exactly what we're going to deal with in the last 5 minutes of the talk. And I had to prove that it was presentable, it was, and the association I written here was actually symmetric monoidal, or at least lax monoidal, which is true. Good. Now, back to examples. Questions? Something I should explain or motivate better? Okay. So suppose you have X, a connected topological space again. Then, as I was mentioning before, you have this notion of locally constant sheaf, right? Which I think I should not explain. I mean, it's sheaf. Let me just write this. So sheaves on X with coefficients in whatever you want. Let me just say in sets. Such that there exists a covering such that so let me call the sheaf F restricted to UE is constant for every I. And you can also formulate this notion in any compactly generated presentable category that would replace sets. But let's not do this. Good. So theorem, and sorry, the theorem is still part of the example. This category, locally constant. Oh, by the way, if X is connected, as in this case, then it's just constant sheaves. Then this is the same as functors out of the category pi1 of X underlined with coefficients in sets or vector spaces, depending on your choice, where pi1 of X is the category having as objects only one point and as morphisms, so home, point, equal to the group pi1 of X. So the fundamental group of X. The group law on this set gives you the composition rule. Good. So this is a classical theorem, already very interesting per se, although now elementary, but very important. And if X is not connected, so let me say theorem again, if X general, so arbitrary topological space, then the same theorem holds with another co-representative functors out of phi1 of X with coefficients inside, but this is the fundamental group weight. And the fundamental group weight is defined as follows: phi1 of X, sorry. Objects are points of X, and hom between 2 points of X is defined to be the set of paths, between continuous paths, of course, between X and Y, so connecting X and Y up to, so quotiented up to homotopy of paths. Okay, I hope this definition is clear. And there is also a derived version of this, so locally constant elements of the derived category and so on and so on. And that involves the fundamental infinity group. Let's get finally to our theorem. So let me say two constructible sheaves. So definition, a stratification of a topological space X is a partition of X into locally closed subspaces. Zi, such that each Zi closure is itself a union of strata. So these are called strata. And I want this. What do you mean, but is itself a union of strata? Well, in general, the closure could intersect other strata, but not be, so other strata intersecting the union, sorry, the closure could be just not entirely contained in this closure. This is not the case here. Okay, and so we denote, so we say that Cj is less than Ci if, of course, they are different, and Zi is contained in the closure of Zj, Zi, sorry. Zj is contained in the closure of Zi. Good definition. A sheaf, so F sheaf on X is constructible if X restricted to Zi is locally constant for every I. Okay, again, sheaf with coefficients in sets or vector spaces or whatever, any compactly generated presentable infinity category or category. Good. So finally, theorem. X topological space, locally contractible. So every point has a neighborhood which is contractible. S stratification, so S is a family of Zi. Stratification of X with properties, so which is conical. I will not give the definition of being conical, there's no point of doing that here. But for example, some of you may have heard about Whitney stratifications. Well, this is an example. Good. This is like requiring that your space as a stratified space is locally similar to some model. Exactly what you, the same thing as you do in topological manifolds. Topological manifolds is, a manifold is a topological space which is all the same everywhere, plus a condition about the change of charts, which is not here actually. Okay, then sheaves. So the category of constructible sheaves, as in the definition above. So the full subcategory of sheaves spanned by constructible sheaves on X with respect to the stratification S, with coefficients in, let me say vector spaces, but also sets is okay. Okay, is equivalent as a category as the category of functors with coefficients in the same thing out of our co-representative, which is called exit XS, and this is a category called the category of exit paths of XS. Okay, as you can see, this is one theorem in the direction we were trying to point out at the beginning, although in a very informal way. And from this theorem, as I was telling you before, you can deduce many things on your category of constructible sheaves, like presentability, like symmetric monodality properties, and so on. If you want, but perhaps let me stop here, I can just tell you what this category is, but only if you ask the question. So thank you so much.
Okay, thank you, Guglielmo. Are there any questions? Oh, we have a in person.
Hey, that was great. So I just have some technical questions because I love this construction. I love the exit path thing, but one thing which bugs me is that you don't necessarily get the right X for the constructible derived category. Like you can't just this. And I'm wondering, so I have two questions. One is if you know of any results which say like, I can refine my stratification in a specific way, and then I will get the right X. So like sort of, you know, if I guarantee that my stratification is made up of k-pi1s with nice properties, do I get that this X problem vanishes? And then my other question would be, how does the like infinity approach solve this problem? Like, is there a very beautiful answer if you work with the infinity exit path category?
Yes. So thanks for the questions. Let me say that this statement I wrote here, in my mind, is actually the derived from, deduced from the infinity categorical statement. So this setting as it is only appearing in some thought of Macpherson, probably. And the thing that has actually been written down extensively is the infinity categorical version that I know of. And so I cannot provide you the exact answer of how the infinity categorical approach solves the problem, although it does. I do not know of any other approaches which are not the one by Jacob Lurie. So Jacob Lurie, same, let me say, same statement, but with derived category, infinity category in this case, of constructible sheaves and exit, so infinity category of exit paths. So apparently, the triangulated category of constructible sheaves cannot really be expressed in this way if you pay attention to what you were saying, that I know of. But if you perform the enhancement to infinity categories, you have exactly formally the same thing. Let me say, so I call this cons xs with coefficients in whatever you want. Let me say your presentable compactly generated infinity category. And this is exactly functors out of the category of X and Fs. There are many generalizations of this. So you can remove some hypotheses here. This has been there's probably many things that I don't know of, but the two things I know of are a work by Peter Hain, who is the person that is using this, is owning this tablet. I think it's 2021, plus also work by Marco Volpe, 2021, from a more, probably this work would answer your question in a more concrete way because it provides application, so 6-functor formalisms. And so how this description allows you to do algebra and talk about 6-functor formalism and Verdier duality for sheaves and constructible sheaves. Yeah, probably this is a good reference. It's called 6-functor formalism with non-presentable coefficients.
Fantastic.
All right. Okay.